You could certainly Google Meet, but you guys could also also watch the lesson because I'm recording them and they're linked up on my website. So here we go. So again, I'm going quicker than I should, but I told you already, kind of quick review of the main things in this chapter is that spontaneous or not spontaneous. Okay. David, can you see that?
Yeah, I can.
Okay, good. So real quick review. I don't want to spend a lot of time, but we talked about this on last Thursday. But kind of the key thing in this chapter is that spontaneous, or again, what they're going to use, the way that they're going to phrase this a week from Friday on the AP test is they're going to say thermodynamically favorable or non-spontaneous. And that's going to be depending on delta G. If delta G is negative, if it's negative, it's spontaneous. If delta G is positive, it's going to be non-spontaneous. And what delta G depends on is this. Okay, and we did these problems in class where we went through and we needed a table and we went through the calculation piece of this. Okay, another part of this was this right here, and the signs on delta H and delta S determine, and temperature determine what the sign on delta G is going to be. And this is the kind of thing I would think you're going to see this, I'm sure, in the Princeton Review, and you'll see this on our test. You'll see this on the mock test. So that's the core of the chapter. That's the number one thing in this chapter. So I'm going to move forward here. And again, I'm going to go through some things kind of quickly here just to save time because I want to move through some of the key ideas in chapter 17 as well and at least get into chapter 17 beginning today. This is nothing to write down, but let's this is an example from a common industrial process is making calcium oxide. And let me see in my notes here. So just explain this. And one other thing too that we're going to talk about today, when delta G is 0, this is when the system is at equilibrium or there's a change in state, meaning, and that you'll see that in a problem we're going to do here this morning, a change of state. But calcium oxide is something that is valuable. I have in my notes here, calcium oxide is used to make concrete, making steel, water treatment, pollution control. Is valuable. It's valuable in industry. And it's the CaCO3 is mined in Colorado. Well, from it, again, in industry, they can make calcium oxide. And so the question comes up for industry, for a business, is to make calcium oxide. Well, again, in a normal year, I would have went back and we would have done the process of solving for delta H and delta S and delta G like we did last week. But again, for the sake of time, what the value that is derived from this is 100. When you do this, the delta G value is 130 kilojoules, positive. It's not spontaneous reaction. And so again, in industry, calcium oxide has value with one of the products, the CaO. So the question is then define the temperature where delta G turns negative, or at least where it's going to be 0. And so in solving for this, the value for delta H, in doing this, the value for delta H is 178.5 kilojoules. And again, the way that was found was this. Delta H is equal to the sum of the delta H of the products minus the sum of the delta H of the reactants, which is what we did on Thursday, which is something that's not a difficult process given the table values. Same thing for delta S. Delta S came out to be 161 joules per Kelvin. So if we get this into kilojoules, so these units are equivalent. So I get that into kilojoules. Well, so in industry, they want to get this to where this is a spontaneous process. So they want to do this. And the question is temperature. So if they rearrange this, so they end up with delta H equals T over delta S. So delta H over delta S equals T. Well, they want this to be at least where this is going to become where delta G is 0. They want delta G to be 0. So they're at least going from non-spontaneous to spontaneous. So if I plugged in the numbers here, so the delta H value was 178.5. The delta S value is 0.161. And when you do that, this would be the temperature where this reaction becomes spontaneous. And it is 1,108 Kelvin, which in Celsius is 835 degrees Celsius. All I'm doing, again, I'm going through this way faster than I should, but I'm showing you in industry how they use this thermodynamic process, and they can figure out a way to make this reaction be spontaneous. So at a very high temperature, this reaction would be spontaneous. Okay, here's another example of that. Okay, so and again, this is nothing, again, this is just kind of repeating what I'm saying. And I know I'm going fast. And remember, everything is really about what's right up here. Right up here is kind of the key things in our chapter. Okay, smelting, removing oxygen from copper or to make copper is non-spontaneous. Copper is something that's very valuable. Okay, they use that in wiring, so making copper. But the delta G is positive. So this is not a spontaneous process. So this is not good for industry. It's not going to happen. So adding carbon to the process makes this reaction spontaneous. So if they throw carbon in here, and now we go back to something we've done quite a bit throughout the year, where now we add up the reaction. So if we add up the left and the right, so the half O2 cancels out, so we're left with the copper 1 oxide plus the carbon makes 2 copper. Now delta G is negative, meaning the reaction is spontaneous. So all that to be said, that these are ways to make, in industry, how they can manipulate a reaction to get delta G to be negative for a spontaneous reaction, either doing it at a high temperature or doing it at a different temperature or adding something else. Okay. Now, this problem I want to do, and there's actually, and I'm going to go over, I want to kind of just walk you real quick through the quiz here for chapter 16 when we're done. But remember, delta G is equal to 0 anytime a reaction is at equilibrium, which includes a phase change. So the question here is calculate the delta S for ice as it melts and for water as it boils. And you have to do this. You have to be given the delta H value. Okay, so let's talk through the logic, the chemistry of what's going on here. So again, when it's a change of state, at equilibrium, the delta G is equal to 0. So delta G is equal to 0, which is equal to delta H minus T times delta S. So if this is equals to 0, then delta H equals T times delta S. But what we're trying to solve for in this problem, it says is to calculate delta S. So if I rearrange again, delta S is equal to delta H over the temperature. So if we're trying to figure out the delta S for ice as it melts. So for ice, and we're given the value here, we're given the HF. So review, HF is the heat of fusion. And and back when we talked about this, we're talking about changes of state. I never understand why they call the heat of fusion melting, but they do, something about melting. So that is this phase change. The HV is the one I'm going to do next. That is the heat of vaporization. So for ice, delta S, and the delta H value here is 6.01 kilojoules per mole. And the temperature that occurs at is, what temperature does melting occur at? It occurs at 0 Celsius. But we want to get this into Kelvin, so in Kelvin it would be 273 Kelvin. And so if I do this on my calculator, so I have 6.01 divided by 273 gives me 0.0220. And what would be the units on this? What would be the units? Does any unit cancel out here? No. So I have kilojoules over Kelvin mole. And if you look back in your notes, that's the units for delta S. Okay. Now normally delta S is always given in joules per Kelvin mole. So if I convert the kilojoules to joules, I just multiply by 1,000, or I move the decimal 3 this way. So 22.0 joules per Kelvin mole. Okay, so the point here in this problem, and there's one like this on the quiz, and I'm going to point this out here when we're done with this chapter. But whenever a phase change is going on, that's what we assume is that delta G is 0. Okay, so then if we do this same thing for water as it boils, so for water as it boils, so again, the delta S is equal to delta H over temperature. So the value for delta H, for the 8, where it says HV, so I'm going to use that. So I have 40.6 kilojoules per mole. And what do I use for temperature? What is the temperature when water boils?
100 degrees Celsius.
100 Celsius, which in Kelvin, good, Tyler, is 373. So if I do that on my calculator, and then I convert it to joules per mole, what I get is, or joules per Kelvin mole. Let me make sure I got that right. Yeah, 109, and it's joules over Kelvin. Okay, so again, and I'm going to point that out on the quiz, and the reason I'm doing that is I think right now my goal is to try and go through as many problems that I think are fair game on the AP test. And so a problem like this, where the where the delta G is 0, is certainly something for the AP test. Okay, final thing in this chapter is this right here. And this is another one of those formulas that is on our formula sheet. I call it the Ratlink equation. And so what's the key thing here is not the derivation, but this right here. Delta G0 equals negative RT ln K. We're going to do a couple of these problems and we'll be done with chapter 16. But this is a problem that is good. One problem of the entire year, I've always come back and go, even the problems I just did, units. I've been like screaming about units. And this is one problem I'll show you where the units really don't work out. One of the rare places. They kind of come close to working out, but they don't exactly work out. So, and again, here we're gonna connect delta G to K, to the equilibrium constant. So another key thing here, delta G is equal to negative RT ln K. And the value we're going to use for R, and again, we're done with test in R class, and so on a week from Friday, they're going to give you the formula sheet without all the writing we've had on it. But if you cared to, so here's the front, on the back, again, thermochemistry, electrochemistry, right there. Again, the Ratlink equation. The value we use for R is the 8.314. And again, right here on the same page, if you look at R, there it is right there. So it's joules over Kelvin mole. And again, I'm going to show you, this is one place where the units kind of don't work out. And I'll show you that when we do this. So using the Ratlink, connecting delta G to K. And I'm going to kind of summarize all this. But remember we said if delta G was negative, then this reaction went forward, which means we'd have a higher value for K. And if delta G is positive, then the reverse reaction would be favored, which means we have a lower value for K. Okay, so here's an example problem. So calculate K. This means KC or KP. So this is capital K. This is equilibrium K. This is not lowercase k, the rate constant K from chapter 13. So we have the reaction. So we're going to solve, first of all, for delta G. So to do that, I'm going to use delta G is equal to the sum of the delta G of the products minus the sum of the delta G of the reactant. So I want to solve for K. This would be a good place to have out your calculator. I was actually doing this last week, and I'll show you kind of how this rounds depending on the number of decimals that I use. Okay, so I'm going to do the products over the reactants. So I've got H2, which the value for H2 is 0, and O2 is 0. So what I've got here is, so the delta G is 1 mole, and the 1 is because the coefficient, well, it should be 2 moles, because the coefficient on H2 is 2, but it's going to be 0. Plus, and then again, I've got 1 mole, but again, the value that I've got is 0. Okay, so these values have to be given, and I've given you those values right up here. Okay, is minus, okay, and then we've got 2 moles of the H2O. So the coefficients, 2, 2, 1. So 2 moles of H2O. And the value for H2O is negative 237. Okay, so if I go through the math here, then what I get, I think, is 474. And it's a positive number, negative and negative. So the value for delta G is 474. And the unit here, the unit is kilojoules. Would you agree with me, for those that are following along? Okay. Okay, so now I want to use, because the question here is to calculate K. So now I'm going to use this. I'm going to use delta G is equal to negative RT ln K. So here's the math. So I'm going to plug this in, but I want to watch the units, because the value I'm going to use for R, 8.314 joules, I want to get this into joules. Okay, so I have 4,704. Like I said, this is one place where the units to me, they don't work out. It's like all year long to me, they've always worked out. And again, this is to me when you guys are doing the AP test, you're doing the mock test, you're doing the Princeton review, is if you ever are bogging down, I would look at the units, and the units will be a guide. So I've got negative 8.314 joules over Kelvin mole. Okay, that right on our formula sheet. Nothing that you had to remember. The temperature here, because it's it says at 25 degrees Celsius. Remember, when you see the superscript 0, that means standard state, which means 25 Celsius, but they give us that 298 Kelvin. and then ln K. Okay, so it'd be great if at least one of you guys would try this on your calculator. Okay, so solve for K. So I'm going to divide the 8.314 off this side and the 298. So again, I'm just doing the algebra here. But now look at the units. And like I said, this is one place where to me the units don't quite work out. Okay, so you follow the units. So Kelvin goes, joules go, and there's really nothing to cancel out moles. Now, so this is one that you just, K, capital K, equilibrium K, Kc, Kp is one of the rare numbers we have that doesn't have any units. And in some would say, well, this is really joules per mole, but it really wasn't joules per mole. So you got to just put that one in your brain to do that. Okay, so this is how I'm going to do this on my calculator. So I'm going to go 474,000 divided by negative 8.314, enter, divided by 298, enter. Now, if I want to take, so I'm trying, this is equal to ln K. So to solve for K then, what I'm going to do, I'm going to go second, which to me means inverse, ln, second ln negative, and I'm going to use the whole number, 191.3163371, enter. And what I get here, and my sig figs, kind of hard with sig figs here, so I guess there's negative 237, so I'll go 3 sig figs. So what I get is 8.17 times 10 to the negative 84. This is a really, really small number. Did anybody do this on your calculator? That's what you got, Samantha. And again, something that I probably haven't done a good enough job throughout the year, but when we do a calculation, I have done this a number of times, is to go back and ask yourself, okay, does that make sense? Does that make sense? Well, if we got a delta G here that's positive 474,000, that means that this is a very positive number. This is a non-spontaneous, a non-thermodynamically favored number. And remember we said if delta G is positive, the reverse reaction is favored, and it must really be favored. So if we look at this number, this means with such an incredibly small exponent, remember K is equal to the products over the reactants. Well, that must mean this number is huge and this number is really, really small, right? Does that make sense? Well, it does make sense. So we have a very, very non-spontaneous, non-thermodynamically favorable, a positive delta G, then the K value would be very, very small, meaning this reaction is going all the way back to the left, right? Right? Think about that. Okay, here is another one. Okay, so calculate the delta G for the solubility of silver chloride and explain why so little silver chloride dissolves. Okay, so for anybody that wants to look at that, I'll give you one more minute and then I'm going to erase this. So this one's a little bit, now we're solving for delta G and we're given the K value. So just, not that we really need it here, and again, it was a big thing back on our chapter 14 test was to always write out the reaction, but if it's saying, calculate delta G0 for the solubility of silver chloride. So silver chloride is AgCl. And so when we put it in water, it's going to break down like this. But they give us the K value, and this thing called KSP, it's still the same thing. KSP, what I mean by that, it's still K. So it's Ag, so what's the products on the top and the reactants on the bottom. This is the top, and since this is a solid, it would be 1. So KSP is really just equal to silver times chloride. SP stands for solubility product, but it's still that concept of equilibrium, products over reactants. Well, we're given the K value. It's 1.6 times 10 to the negative 10. That's a very low number. Meaning there's not very much silver and chlorine in there. Okay, but the point of this problem is to solve for delta G. So I'm going back to the rat link. I'm going to use the rat link. So rat link connects delta G to K. So here I've got negative 8.314 joules over Kelvin mole. Temperature is, and again, it doesn't give a temperature, but when it gives this superscript 0, it's telling you it's standard state. So that's 298. And Ln, and we know K. They told us K, it's 1.6 times 10 to the negative 10. Okay, I'm going to do this on my calculator. I would recommend you to try it on your calculator. I'm going to start out with the Ln. So I'm going to go Ln 1.6 second exponent negative 10, enter, times 298, enter, times negative 8.314, enter. And this is what I get. Make sure I got this. I get 55,883. Okay, the unit I would have here is Kelvin goes. So technically, this would be joules per mole. Would you agree? Would you agree? In terms of the units, joules per mole? I think so. Wouldn't you say? I think so. Alex is one confirming this. And then we always go back to sig figs at the end. And the only number I'm given is the KSP, which has 2 sig figs. So I'd go to 2 sig figs, and I would probably just get that into kilojoules. 56 kilojoules.
So wait, why is it 5 degrees Celsius?
Say it again.
Why is it 5 degrees Celsius?
It's well, it's Celsius. It's 25 Celsius. It's because they give it as the superscript 0, and that means Tyler's standard state. And standard state meant that the pressure was 1 atm, which isn't a factor here, but the temperature was 25 Celsius. Okay. I think that is going to conclude this chapter. I told you one thing that I think would be a really good thing to do is, or if you're confused at all, is to go back, and there's that Bozeman science chemistry teacher in Bozeman, Montana, and to look at his stuff, and that might be a good thing to do. Again, I'm going to erase this here. One minute. Did anybody else? Somebody confirm that you got that? We got that. Okay. Units make sense. Would you agree? Units make sense. Okay, so here going back to, and this will conclude the chapter. And then again, if you guys have the quiz out here, I'm going to talk about the quiz, but this again comes from the Bozeman Science Guide, but kind of relating free energy, which is delta G. So to me, this was a good summary, and equilibrium constants, which is K. So if we have the reaction, so thinking about this thermodynamically, and then thinking about this with equilibrium, and how these are connected. So for delta G, and this is K. So if this is 0, then this would mean that this is 1. And this is at equilibrium. If this is negative, it means it's spontaneous, and the K would be greater than 1. And if this is positive, then the K would be less than 1. So this would be a spontaneous reaction. This would be a non-spontaneous reaction. This would be favorable in the forward direction. This would be in the reverse direction. And here's another term that it comes in here. And to be honest with you, I'm just going to tell you this. It's a weekly Friday. If you see it, great. Exergonic means giving off energy. Kind of like, to me, kind of like exothermic. But you see exer giving off. So if you see that term, you know, if you can remember it, something just to put in your brain. And that really concludes this chapter. The last thing that I always go over in this chapter, which again, for the sake of time, I'm not going to waste time, but it's about the thermodynamics of a rubber band. And the question, I always throw this on our chapter 16, 17 test, but do the strands of rubber band, is there a lot of disorder or are they ordered? Well, one thing about when you stretch a rubber band, you go back to this. When you stretch a rubber band, if you stretched it a bunch and you put it up to your lips, something that's sensitive, you would see that it gets hot. It gets hot. So if it gets hot, what does that mean? It means that it's exothermic, so it's negative. And when you stretch a rubber band, is that a spontaneous process or not? Is stretching a rubber band, does that just happen without a plan? No. So the delta G would be positive. So we have a delta G positive, and then temperature is really not a factor here. So delta S. So if we have a positive delta G and a negative delta H, the question is then, what is the story on entropy? So temperature times delta H is equal to delta G minus delta H. So if this is positive and this is negative, delta G is positive, delta H is negative. What must that mean about delta S? So we have a positive and a negative and a negative.
Positive.
Positive. And so a stretched rubber band has a positive delta S, which means that it is, am I right about that? I got to read that again. So if I have a positive, I didn't write this right. So if I have, it should have been like this. So delta H, I didn't do my algebra right, is equal to, so if I algebraically rearrange this, so delta H is equal, temperature times delta S is equal to delta H minus delta G. And if this, the symbol for this is negative, and the symbol for this is positive, then the delta temperature times delta S has to be negative, which means that the disorder is decreasing. So a stretched rubber band has more order or less entropy. Okay, real quick on your quiz. If you have your quiz out, let me just real quick talk you through some of these things. I think number one, we talked about in terms of all I want. Does everybody have quiz on chapter 16? Everybody's good? And again, I will post the answers to these on I'll try and do it today on both Canvas and my website. So number one, all I care about is the sign, positive or negative. Number two is just making a prediction. Okay, so number three, this one's a little bit confusing. It says elemental mercury is a silver liquid at room temperature. Its normal freezing point, so we're given its freezing point, its molar enthalpy of fusion, so it's to melt it, it's 2.29 kilojoules. What is the entropy change? Because it's a change of state. So because it's a change of state, on number three, we can say that delta G is equal to 0. So because it's a change of state, we can say that enthalpy is 0. So what we get here is delta G is 0 is equal to delta H minus T times delta S. And what we're asked for here is we're trying to find the enthalpy change. So delta H is equal to temperature times delta S. So delta S is equal to delta H over the temperature. Okay, so, but the key, so that's kind of one key. There's two key things in this problem. That's one. But the other thing is because we're given the heat of fusion and we're given it's 50 grams of mercury. I've got to convert those grams of mercury to kilojoules, and that's where I'm going to use the 2.29. Okay, so you're going to have to do that conversion, and that's the number you're going to plug in here for delta H. And again, I'll leave the answer key here, as well as I'll leave the answer key, or I'll post it, like I said. Number 4, you're going to use the appendix in the back of your book. So if you look in the back of your book, you can look up the delta S's. So you might want to write yourself a note, just like it says there, look in the appendix in the back of the book. Number 5, again, what you're going to do here is you're given, well, that one's easy. Hopefully that one's not a problem. You can just plug in the delta H and the delta S, make sure the units are right. Number 6, again, you're going to use, and I think you've already got the values there. See, I think there again, you got the values. You can use the appendix in the back of your book. Number 7 is all about the signs. So about the positives and negatives, and to go from there. Number 8 is another one that's this. Okay, so number 8, so if you write the reaction, so all we're doing is we are boiling it. So we're going from the liquid to the gas. So for 8A, you go from liquid to gas. B, the delta G is 0. So then for C on number 8, we're going to get to this. But what we're going to do here, we're trying to solve for temperature. So temperature is delta H over delta S. And you got the values there, I think, to solve for delta H and delta S. Okay, number 9 is a rat link. We just did that. Okay, so that should help you on all that. So, okay, so we are done then with chapter 16. And again, quizzes due. And what I want to do now is, first of all, it's something I wanted to do back at the beginning of class, which I forgot to do, which is about our shirt. Okay, so I want to go. This is what about the shirt thing, and I need to get an order made. Here, I'm going to do this. So I need to get an order in here for those that want to do this, and I'm going to do it. Okay. So there we go. And David, I'll try and get this up for you too. But I really, because if we're going to have the shirts, and now because we're not going to meet tomorrow, it's really important to get this done today, try and get our orders today. Okay. David, I don't know, can you see that?
Yeah.
Okay, so there's the front. We kind of already talked about it. There's the back. We corrected this. Okay, so what I need to do is I need to see who wants this. And the sizes we're going to do is just going to be just min sizes, just small. I don't know. Anybody would need extra small. But I'm hoping if I get the order in today that I can have this early next week. So let me start. Just all I'm going to do is pass around. The cost is going to be $12 a shirt. And again, I don't know. I just always think it's kind of a good thing. Jeez, I'm having problems today. And so just sizes just like you would get at a store. And again, this is something I don't want anybody to feel obligated to, but if you want to, you can do. So I'm going to pass this around, and David, you can tell me if you want to order one or not when class is over. So just pass this around to everybody. Again, if you're not interested, but it's $12, and I just need the $12 either later this week or early next week. So any questions on that then? You okay with that? Okay, then I want to get into chapter 12, or chapter 17, I mean. We're actually going to start out chapter 17 with review.
Is 17 on the page?
Yeah, it is. And again, it's stuff I think, Tyler and everybody, it's stuff that if we spend time on it, I really think we can get it. Whoops. David, can you see that?
Yeah.
We can? Okay. So here are the problems for chapter 17. So you're good, David? You can see that?
Yeah, I can see it.
You guys could just pass that around the room. And I know, like, Mason's not here today. Juliana's not here. I know it's senior ditch day. If David's not here, is there anybody else? Who else? And Lauren and Allie is not here either. So I need to contact them. Oh, no. Okay, so we're going to move into chapter 17 now. And there's going to be review first of all here. David, you can see that? Yes?
I don't think so anymore.
You can't? Okay.
It was there for a second.
Okay. Let's do it again. Can you see it now, David?
Yeah, I can see it.
Okay. So, and again, you guys are at the point where you don't need to do textbook problems, but if you wanted some practice on this stuff, and notice here in these problems, we're actually today, I want to get through two things. I want to do review from what we did back in chapter 4. So you can see here are the problems, and I've given some problems from back in chapter 4. What this chapter is about. This chapter is about electrochemistry. And the key thing, kind of the basis of electrochemistry, is the idea of reduction oxidation. So we're going to review reduction oxidation today, which is a good thing to review anyway. And again, I'll get out the quiz here. Matter of fact, I'll go get it here. I'm going to put up the next slide. So we're going to spend the next few minutes doing review. And then I want to look at a galvanic cell. And once we get done with that, I'll go ahead and stop. And then on Thursday, Thursday is a key day to really get through a couple key things in chapter 17. But this is again about electrochemistry. So this is how a battery works, how a chemical reaction can create electricity. So again, there are the problems. Okay, so let me just put this up. This is quick review, and I'll leave this up. This I actually just copied right from chapter 4. And it's stuff that we did before. But first of all, assigning oxidation numbers. And it's really closely connected, just quick review, it's closely connected to ionic charges. Okay, so I'm going to leave that up for a second for whoever wants to take notes. Okay, like I said, I'm going to put up here the quiz and the review I have for chapter 17. And again, today we're going to, again, start covering main points, and then we're going to continue this on Thursday. And if you care to pick it up today, fine. If you want to pick it up on Thursday, the quiz for this is going to be due, and I'm going to do the same thing. I'll post the answer key next week for it, but it'll be due next Tuesday, a week from tomorrow. We'll be in May. Tyler, graduation, which we talked about so long ago in homeroom, is coming up now. Do you remember me ranting and raving about that back when you were in homeroom? Do you remember that? I said, because there were so many that didn't, they didn't want to, or they seemed like they weren't aware that you had to have certain credits to graduate, to get through school. And if you think about that homeroom, there's a lot of people that were in there. They're no longer in our school. I don't know where they're at.
You managed to lose a lot of kids.
I did. We lost a lot of kids. So, okay. So assigning oxidation numbers, oxidation reduction reactions. These reactions involve the transfer of electrons from one substance to another. It's always abbreviated redox. So first of all, assigning oxidation numbers, and this is the way I teach it in first year chem, again in a normal year, which of course we didn't have last year. We haven't had this year. But so my chemistry students of this year are not going to get this. And just like those that I had, or you guys in Mr. Conyers and Mr. Hodis' class, you didn't get it last year either. But lone elements, their oxidation number equals its charge. So if we have, like we're here in a second, we're going to do O2. And I'm going to say almost all the time in a compound, oxygen its oxidation number is its charge, which is -2, with the exception of a peroxide. But when O2 is by itself, when something is by itself, its oxidation number equals its charge. Then oxygen in a compound is -2 unless it's a peroxide. And two peroxides to watch for are this one and this one. And kind of the key is when you see, or this one here, when you see a 2 here with oxygen with oxygen, you see a subscript 2. I mean, hydrogen's a positive one, so this would have to be a 2. So again, that's rare. But you guys are taking the AP test a week from Friday. So the Patriots, it's like playing the Patriots. They're always good. They're always good. But the Broncos actually beat the Patriots last year, and the Broncos were bad. So the Patriots finally weren't that good. But typically in a compound, oxygen's -2. Hydrogen is +1. And then the oxidation numbers need to total the charge on the ion or the molecule. Okay, and I'll look at that today too. So, and then finally use the ionic charges of the elements if that's the last thing. So we're going to figure out what's been oxidized and reduced. But what I mean by that, so let's say that we're going to assign the oxidation numbers. Now this is review from way back in September, but for oxygen and sulfur in sulfate ion. Well, oxygen is -2. Again, rule number 2, in a compound or an ion, oxygen is -2 unless it's a peroxide. So then what is sulfur? So oxygen's -2 times 4 is -8. Now each oxygen is -2. Each oxygen is -2. Overall it's -8. And this is what I call fill in the blank. It needs to total the charge. So then what does sulfur have to be? What in -8 equal -2? Well, that would be +6. Okay, so assigning oxidation numbers. How about if we've got this, nitrogen trioxide, no charge, no charge. So the oxidation number for oxygen, again, is -2. What is nitrogen? Well, this, because it does not have a charge, needs to total 0. The oxidation numbers in a compound or an ion always need to total the charge. So then oxygen, -2 times 3 is -6. So what does nitrogen have to be? What does nitrogen have to be? +6. Okay, so that You guys good? Remember this? Remember this? Okay, and then I had these couple little sayings, and I'm going to get into some others, but I have, thank you very much. I appreciate that greatly. Thank you. Is Leo, the lion, goes grr. You guys may remember, may not. Loss of electrons is oxidation. Loss of electrons is oxidation. Gaining electrons, reduction. Gaining electrons, reduction. And then another little saying I had, what are those called, Chloe? Mnemonic devices? I'm a redneck. I don't know what that means, but I know these are easy ways to remember things. That's the way I remember it. So, sorry, Jackson. I actually got the word right, didn't I, Chloe? Mnemonic device.
If you want to have some real fun, though, ask someone to spell mnemonic.
Oh my gosh, there's no way. I don't even know what letter it starts with.
It's N.
It starts with an N?
Yeah, it's N-M. Really weird.
But oil rig. David and Kyle over there, they're looking at me and going, that guy is a loser. Oxidation is loss. Oxidation is loss. Reduction is gain. Reduction is gain. Okay, so I'm going to assign in both these reactions, we're just going to figure out what's been oxidized and reduced. So I've got CH4 plus 2O2. And actually, in doing these, the subscripts do not factor in at all. The subscripts don't factor in at all. Plus CO2 plus 2H2O. Okay, so I'm going to assign oxidation numbers. So I know by rule number 3, hydrogen is a positive 1. So what is carbon? Well, because there is no charge, this needs to total 0. And hydrogen's positive 1, so it's positive 4. So again, fill in the blank. So positive 1 times 4 is positive 4. Now, every individual hydrogen is positive 1. Overall, it's positive 4. So then carbon is negative 4. You okay with that? I'm going fast, Kennedy. Hopefully I'm not going too fast. Am I going too fast? No. Like I mentioned here, 0 for oxygen, or O for oxygen, is 0. When something is by itself, including oxygen and hydrogen, its oxidation number is 0. So then we have the arrow. So over here, oxygen is -2 in a compound, and this needs to total 0. So -2 times 2 is -4. So what would carbon be? Positive 4. And here in a compound, hydrogen is positive 1, oxygen is -2. So I have positive 1 times 2 is positive 2, -2, 0. Okay, now compare the left to the right. I always remember it this way. This is, and again, I taught you this back in September, is that to me, I like to shop at Walmart because they reduce the prices. They reduce the prices, so they go down. So something that is reduced means its oxidation number has decreased. In this case, that is oxygen. So this has been reduced. 0 to -2 is going down. That's been reduced. And then, so then the opposite of that is what is oxidized. So that is the element whose oxidation number went up, which was carbon. So carbon was oxidized. Remember this? Okay, let's take a minute. Try B. So we have Fe2O3. So you want to assign oxidation numbers for everything. So assign oxidation numbers for everything. And then tell me what's been oxidized, what's been reduced. See if you can do it. Again, did this a long time ago. See, Lauren's not here, Allie's not here, Mason, is there anybody else I'm forgetting? And David. David's, though he's Google me. And Kara. Kara's not here. Write this down so I can remember this. Kara, Warren, Allie, David, Lisa. Okay, and if for some reason on the shirt thing, if you change your mind, I'll probably put in the order tomorrow because I need to contact these people. If you change your mind and you signed up and you don't want it, or vice versa, you didn't sign up and you do want it, let me know. Either come by today, Access, or send me an email.
It's $12.
It's $12. $12. And it was actually like $11.65 or something like that, but we'll just round it to $12. Okay, so here, oxygen is -2, always in a compound. Needs to total 0, so -2 times 3 is -6. Now, iron, you gotta look at this, okay? Iron is +6, right? But there's 2 of them, so I'm gonna take 6 divided by 2, so each iron is 3. Okay? Here, oxygen is -2 in a compound, again, needs to total 0. Remember, we ignore the coefficients. One place we ignore the coefficients. So then carbon would have to be a +2. Good with this? Okay, here, iron by itself is equal to its charge, which is 0. Here, oxygen is -2. Needs to total 0 because there is no charge. So -2 times 2 is -4. So fill in the blank. So carbon is positive. Okay, so in every case, one element should go down, one element should go up. So in this case, oxygen didn't change, so it was neither oxidized or reduced. But iron went down from +3 to 0, so it was reduced. And carbon went up, so it was oxidized. And it's good, just good review. And the point here is what happens is there's a transfer of electrons, which can create electricity. Okay, the next thing, now balancing reactions with the half reaction mechanism. Okay, and this is again something that we did. So I want to go over this review, and I want to talk real quick about this thing called the galvanic or voltaic cell, and then I'll stop. But I want to go over this. Just, it's good review, and it's definitely a good possibility a week from Friday. This will be on your guys' test. And I'm going to show you here how I do this. Again, here are all the notes I gave back in chapter 4, and I'll slow down. I'll give you a minute to write it down. And we're going to do a couple of these. And actually, when we came to this in chapter 4, back about mid-September to late September, all we had done up to that point was review. Not that it was easy, but we had reviewed over and over and over again. Moles, stoichiometry, balancing equations, writing formulas. And this was the one place where we really got into new things. But here are the steps that I always use on this. So kind of to simplify this is I always balance the elements. So here's a shorthand way. Other than oxygen and hydrogen. Because that's always my step 1. So we're going to do these 2 down here. So at number 1, it looks like Fe and Mn are already balanced, but 2, I'll have you guys do 2. Chromium's not balanced. So that's number 1. Okay, then step number 2 is we're going to balance oxygens using water. Okay, back when we first learned to balance, we always said, well, I always taught my classes, you always save oxygen to the end. Not so here. It's actually the second step. Okay, then we're going to balance hydrogens with H+. And then the place where I always make a mistake, hopefully I don't today, is I'm going to balance the charge with electrons. And again, I got to keep track of the charges. So here's, again, this is the shorthand way to do this. And then finally, I want to get the electrons equal, and I total the reaction. So balance the elements other than oxygen and hydrogen. And technically 1 and 2 are good to do, or really 1, but usually when you look at a reaction like 1 and 2, usually the elements that you look at are the elements that are not oxygen and hydrogen. So if I look at reaction 1, so I've got Fe plus 2 plus MnO4, and of course the really right way to do this is to do what I got there in step 1, which is to look at the oxidation number. So I can see that iron has been oxidized. So there's 1/2 reaction. So plus 2 plus 3, that's really easy by inspection. Here, Mn's plus 2, and here, oxygen -2 times 4 is -8, so Mn would be plus 7, so it was reduced. So here is the reduction part of this. Okay, so here, let me go through this one. I'll have you guys do the next one, and I want to talk real quick about these voltaic cells, and then I'll quit. But first of all, so I'm going to balance the elements other than O and H. Well, iron is balanced, Mn is balanced, so they're good. Okay, then I'm going to balance oxygen using water. There's no oxygen here, so I'm okay, but here there's 4 oxygens. So I'm going to need 4 waters. The reason I need 4 is there's 4 oxygens. So it balances the O. Okay, then I'm going to balance hydrogens with H+. Well, again, there's no hydrogens here, but here there's 4 times 2, 8. So I need 8 hydrogens. Now where I always break down is this. So I'm going to balance the charge with electrons. Remember, electrons are negative. Okay, so plus 2 plus 3. I want to get the charge equal, so I'm going to put 1 electron there. By doing that, I now plus 2 and plus 3 and -1 is plus 2, so the charge is equal. Here again, I got to watch this. So I have plus 8 and -1. So I have a net plus 7 here. And here I have plus 2. Plus 7. So again, I want to get those charges equal. So again, electrons are negative, so I'm going to have 5 here. So 5 and -7, or 5 and a positive 7 give me -2. Okay, then I'm going to get the electrons equal in both reactions. So I got 5 here, I've got 1 here. So I need to multiply this whole thing through by 5 because I want to get the electrons equal. So 5, 5, 5. Now I'm going to add this up. So the electrons cancel out. And again, if I had something else, in this case I don't, but something that was on the left and the right, I could cancel out. A lot of times water, or I could simplify it, but I don't have that here. So what I get then is 5 Fe plus 2 plus 8 H pluses plus MnO4 negative makes 5 Fe plus 3 plus Mn plus 2 plus 4 waters. Do you remember that a little bit? Doing that? Okay, you guys try B. Error 2. Cr2O7 -2 plus I negative. Okay, go ahead and take a minute. See if you can go through and write out what you're doing is you're using the half reaction method, balance this reaction. So if I locate here, so what I'm going to have is chromium. So I'm going to have Cr2O7 -2. It's going to be 1/2 reaction. And the other one's going to be iodine. So first of all, I identified what's being oxidized, reduced. Technically, I know iodine going from -1 to 0, that's an increase, so it's being oxidized. So the chromium would be reduced. But anyway, so there we got that. Okay. So balance the elements here. This is sometimes a mistake I make. So 2 chromium, so I got to do that. That'll be important. And 2 iodine, so I need a 2 there. Okay, balance oxygens with waters. So here I have 7 oxygens, so 7 waters. No oxygen there, so I'm okay. Balance the hydrogens with H+. So there's no hydrogen, or there is hydrogen here. There's 7 times 2 is 14. But there's none here. Okay, and then this is always where I make my mistake. So I balance the charge. So what I've got here is I've got 14 positives and -2. So I have a net positive 12 on this side, 14 positives and -2. And here I have positive 6. So that means I'm going to have 6 electrons here. And here I have -2, so I'd have 2 electrons. Okay, now I'm going to get the electrons equal on both sides. So I want 6 on both sides. So I'm going to multiply this through 6. So I get 6, 3, 6. Okay, so if I add this up, now, so what I would have then is I have 14 H pluses plus Cr2O7 -2 plus 6 I negative. So I have this, this, and this. And on this side, I have 2 Cr +3 plus 7 waters plus 3 I2s. Questions there on that? Okay, last thing real quick, I'm going to talk about this just briefly, and then this is where we're going to get into. We need to have a very productive day on Thursday. Okay, electrochemical cells. Okay, and this might be worth noting. Okay, this is something you can see on the AP test. I'm going to talk here just briefly for a minute. It's where I'm going to pick up on Friday is a galvanic or a voltaic cell. And it's one of the key things in this chapter, kind of the number one thing we're going to get to on Thursday in this chapter is calculating for E0. But we kind of had to do what we were doing today, assigning oxidation numbers and writing out half reactions, getting the concept of a flow of electrons going from one thing to another. But a galvanic or a voltaic cell which is spontaneous reaction. Actually, we'll get to on Thursday, but we're going to connect what we did earlier in class today, delta G to K, to this thing called E0, which again, we haven't talked about, but we'll talk about on Thursday. But a galvanic or a voltaic cell is a reaction that spontaneously occurs. An electrolytic cell, which will be actually the very last thing I'll talk about, the very last notes I'll give you this year, I think, will be on a electrolytic cell, which is a non-spontaneous cell, so an external source. This is how they charge batteries, is with an electrolytic cell. And again, I'm going to show you a problem that it'll be the very last problem in this chapter. And again, Thursday, we need to have a productive day on Thursday going over this. But the difference between a galvanic cell, which again, I'm going to put up here in a second, I'm just going to talk about briefly and then I'm going to be done with it, versus a galvanic cell or voltaic cell, which is a way, like a battery, a way to create energy, versus an electrolytic cell, which is a reaction that does not create energy. Okay, so let me put this up here for a second. this is, and again, this is where I'm going to start on Thursday, but this is definitely a key thing. This is a electrochemical cell, and it looks a little overwhelming. But let me just talk about it, and I'm going to come back to this again on Friday. But what happens is this. So they have two cells. One cell where oxidation is occurring, and they call that the anode. Okay, and so oxidation means electrons are lost. So in oxidation, it's like this. So we have X makes X plus 1 plus an electron. Electrons are lost, the oxidation number goes up. So electrons are being given off. And in this cell, that is what's going on here, is electrons are being lost. And so what happens is this metal, this metal plate of zinc is actually deteriorating, and it's turning into this ion, but it's giving off an electron. So one cell is the anode. Think of valves. Anode oxidation is occurring. The other cell, cathode, it's called the cathode, is where reduction is occurring. So if I have what's going on, so this is an anode. This is where oxidation is occurring. So the cathode, where reduction is occurring, would be like this. So we have plus an electron plus Y, so we get this. So what we're doing here in this case is we are making, we're making a charge, something that is negatively charged. And so, and actually what's happening here is we take at the cathode is we're going through oxidation. And so actually what's happening is that the electrons are flowing from the anode to the cathode, and we get a flow of electricity. And again, the key thing in this chapter is going to be to calculate this E0, and it's not a hard process, and I'm going to teach you that on Friday. So a galvanic cell is a cell device that produces electricity by spontaneous redox reaction. Reactions must be separated from each other. Anode is the electrode where oxidation occurs. It's the mass decreases, and that's always, and when I give the test, which of course I'm not going to do for you guys, but I always have that as a clue on the test. So at the cathode, the mass is going to decrease. Well, that makes sense because it's going down. And the electrode where reduction occurs, the mass increases. And this is, here's a couple little of these mnemonic devices. We had Leo the lion goes grr, an oil rig. Here, an ox cares. And actually a student I had like years ago, Jackie Becker. But anode, oxidation, cathode, reduction. Anode, oxidation, cathode, reduction, and ox cares. And another little mnemonic device I have is fat cat. Fat cat, meaning the electrons go from the anode to the cathode. From the anode to the cathode. And then the final thing is the salt bridge, which is this right here. What it does is it allows the charge to remain constant. So I always remember it this way, is that in the salt bridge, we have anions and cations. The anions flow into the anode. Because over here, and you guys can't see it, but we're having a buildup in the anode, we're having a buildup of positive charge. And so because of that, we need a negative, an anion to come in there. So the anions from the salt bridge go into the anode, and the cations go into the cathode because we're having a buildup of negative charge. So, okay, I'm going to stop there. I'm going to actually come back. I'm going to see if I can find just a short YouTube video. But Thursday needs to be a productive day. But again, I have the answer key here. Again, this chapter 17 stuff you guys can get on Thursday as well. So, okay. Okay, David, I am done. David, do you want a shirt or yes or no?
Sure.
What size do you want?
Large, please.
Okay. Okay, David, well, take care of yourself, buddy. So you want a large?
Yes.
And hey, Thursday we'll Google Meet again. And what you guys should be working on is you guys should be working on your Princeton review. You can be working on the quiz. The Princeton review is really important.